Hello everybody, welcome. And today we're going to use synthetic division to find the zeros of the polynomial function. So here we have our polynomial function 3x squared plus 5 minus 2 equals 0. So for this function, our divisor would our divisor would be x plus 2. So for synthetic division, we will be using this table. So basically, to fill up this table, you will need to add the numbers from your polynomial equation. In this case, ours is 3, 5, and negative 2. Make sure you don't forget the negatives, such as this one, as it will cause you to make mistakes during synthetic division. Alright, so our divisor here would be x2. Since we are dividing, we all know that the positive 2 will then turn to a negative. So now that we have set up our table here, I'll explain what we're going to do. So basically here, what happens is that the number will drop down here. So we're going to drop down 3. And so basically for every number that is here at the bottom will be multiplied by the divisor, which is negative 2. Which gives us which will then give us the product of negative 6. So what we're going to do is we're going to divide like normal. We're going to subtract from normal. So 5 minus 6 would equal negative 1. So again, we repeat negative 1 is negative 2 equals 2. So we're going to subtract again like normal. Negative 2 plus 2 equals 0. So we have found a 0 in in using synthetic division. The final row of the synthetic division shows the coefficients of the resulting linear equation, which is this. This is our equation. In this case, would equal 3x minus 1, which can which means that which oh no, oh no, it's flying, which means that our equation, which means that our equation 3x squared plus 5x minus 2 equals 0 could be can be simplified into the following, which is parentheses x plus 2 and 3x minus 1 equals 0. So in this example, what we basically did is we divided the polynomial by x plus 2 to find the clear x value for synthetic division. The value used at the divisor is negative 2, which is a root of the equation. All right, so now we're back with our second equation, which is graphing a general equation. So we have g equals negative x cubed plus 1/2 x minus 7. So when when graphing the general equation, we're going to look at the we are going to look at the degree and leading coefficient. So the degree is usually the little number up here, which in this case it's a 3, meaning that the equation is cubic. We also know that our leading coefficient, uh, no, we also know since it is a cubic, it has a maximum of 3 roots, which means it could intercept the axis a maximum of 3 times. But it doesn't necessarily have to have contact with the axis 3 times. It's just a maximum amount. So let's say we could have, oh, I should probably change the color. Okay, change it to yellow. Alright, so here are some examples. Give 3 examples. So, by what they mean cubic is that it could touch the axis 3 points, or it doesn't have to touch at all. It just means, you can have a maximum to 3 points. So, it could go like this, like this, or like this. You see how this one doesn't touch, the turning points don't touch the x-axis at all, while these two do. So we can count it 1, 2, 3, 1, 2, 3. Well, this one only has one contact. Alright. So we also need to look at the leading coefficient. So over here, our leading coefficient for this equation is negative 7. So that would be so it'd be written like this. And that is a point of contact on the y-axis. So the y-intercept is the point where the graph intercepts the y-axis. In this case, the intercept is 0, -7, meaning it passes through the point of 0, -7. Self-explanatory. So, the next thing we need to the next thing we need to look at is the turning point. That would be B. And this one, that would be these. See how the graph changes here, goes up again, and goes down. This one goes down, changes to up, and turns down. And so we really can't do that at the moment because it's just like a general graphing of the equation. You would need to have the derivative of it. But like we can't do that, We don't have all the information yet. And the last thing we need to look at is the end behavior. Since the leading coefficient is again negative, it means that the graph would be negative. So this is negative. The ending coefficient will be approaching negative infinity, which means it could possibly look like this, you know, or it could look like this. And so that is basically graphing the general equation. So, um, uh-oh. So now we're going to resume and check whether our predictions were correct. So our equation is gx equals negative 7x cubed plus 1/2 x minus 7. So you can see here our prediction was correct. It does. It is one of the ones we were predicting. We see that it only crosses the x-axis one time. You'll see that it does change points 3 different times. So 1, 2, 3. You can see that it crosses negative 7 and that the ending is approaching negative infinity. Yeah, that's about it for this one. All right. Which then brings us to our last problem. So this is the real world application problem. And it says a company is manufacturing selling widgets. The cost to produce it X widgets can be modeled by the polynomial function Cx equals 2x squared plus 5x plus 100, where x represents the number of widgets produced and Cx represents the total cost in dollars. It's asking, what is the cost to produce 50 widgets according to the given polynomial function? So here is our polynomial function. And so here the equation is telling us that we need 50 widgets. Oh, we need 50 widgets. So that's going to be our x. So x will equal 50. So basically for this equation, all you have to do is plug in x into the equation. So that would be here and here, which which gives us the equation. Oh, wait, I should change it like this, which gives us the equation Cx equals 2, and then it'll be 50. All right, and then plus 5, and then that's where the 50 goes, plus 100. All right, all right. So basically what happens here, you just plug in the numbers and you go in as follows. So let's change it to a new color, which will give us, which will then give us 2 parentheses 500, well, 500 plus 250 plus 100, which will then equal to 5,000 plus 250 plus 100. Oh, there, which will then equal to a total of 5,350. Therefore, the cost to produce 50 widgets according to the given polynomial, which is this, is $5,350. And yeah, that's about it. Here we've done our three. First we use division to find the zero and see whether or not it's a linear function. We use the graph to we use the upon equation to graph the general equation. And finally, we apply the real world problem using function. I think that's it for today. Thank you very much. Um, and yeah.